You're probably pretty familiar at this point of how to solve two equations and two unknowns. Let's say we had the equation 2x, I don't know, minus y is equal to 10. And let's say you had x plus 3y is equal to 5. There are a lot of different ways to solve it, and visually, the representation we use in our heads is that this represents a line and this represents a line, and if they're not parallel to each other, they're going to intersect in a unique point, and that unique point will be the solution. That unique x and y will be the point where these two lines intersect. And so one way that we can solve these is we can multiply either of these equations by scalars, by numbers, and we'd have to multiply both sides of the equation and then add them to the other equation. So what we could do, and we do it in such a way, is that we eliminate variables. So for example, if we wanted to get rid of, let's say we wanted to get rid of the y term. So we could take this equation, and then add it to what? So we have a 3y here. So then if we made this into a minus 3y, when you add the two, you would get 0. The y's would eliminate. So let's multiply this equation. Well, actually, let me do it this way. If you multiply this top equation by 3, you get 6x minus 3y is equal to 30, multiplied both sides by 3. And the bottom equation, we're keeping the same. X plus 3y is equal to 5. And then you just add the two. So 7x, that's 0, is equal to 35. I picked these numbers at random, but it seems that they actually work out. So we get x is equal to 5. And then you could go back and you take this and you could substitute it back into either of one of these equations. So you would have, let's do the first one, 2 times 5 minus y is equal to 10. 10 minus y is equal to 10. Y would be equal to 10, right? 10 minus 0 is a 10. And it's true here in this equation as well. So that's how you solve two equations of two unknowns. So how do you do it with three equations? So I have here, let me write it down. I designed this equation so it's actually reasonably straightforward to solve. So you have minus x plus 2y minus z is equal to 9. I have 3x minus 7y minus 2z is equal to minus 20. And I have 2x plus 2y plus z is equal to 2. Now, first of all, what's the visual representation of this? And if you watch the intuition, when I talked about the video on the intuition of a three-variable inequation, you know that each of these represent a plane in 3 dimensions. And so if you're trying to figure out what x, y, and z satisfy all 3 of these equations, you're essentially saying what point in 3-dimensional space exists on all 3 of these planes. And that point is essentially the intersection of these 3 planes. And that's very hard to draw, so I won't do it now. But you might want to watch that visual intuition video I did. But anyway, let's go to actually solving it. So solving it, 3 equations in 3 unknowns, you actually do the same thing as you did with 2 equations and 2 unknowns. It's just a lot messier, and it's just a little bit more confusing in terms of which variable do you need to eliminate and when. And because of that, it's very, very, very important to be systematic about it. So the way I like to do it is I like to, let's say, keep, and this is actually called Gaussian elimination or Gauss-Jordan elimination, and it's done a little bit more formally in linear algebra. But essentially, I like to eliminate the 2 x's in these 2 equations, and then I like to eliminate this y in this equation. So all you're left is with a z here, and then you'd have z equals something. Then you could substitute into this equation, and then you could solve for y, and then you could substitute the y and the z back into this equation and solve for x. So let's do that. I know that sounds a little daunting, but I think if we actually do the problem, it'll be a little bit more straightforward. So before we break into the mechanics, I want to show you something else, and this is, depending when you're doing this, your teacher might be upset or impressed that you do this, but this is just an easier way to save time, is to write an augmented matrix that represents these three equations of three unknowns. And what do I mean by that? Well, we're going to be rewriting these over and over again. And instead of writing a an x, a y, a z, and the equal sign every time, let's just write the numbers that matter. So we can represent this as, so minus x, we could say this is minus 1, 2, minus 1. And this is called an augmented matrix, because we'll put a 9 here. So this just says minus x plus 2y minus z is equal to 9. And then we say 3x minus 7y minus 2z is equal to minus 20. I'm not doing anything here. I'm just rewriting it in a form that has a little bit less letters in it. And then the last equation is 2x plus 2y plus z is equal to 2. So the first thing I said that I wanted to do is I wanted to eliminate these two x terms, right? And these, remember, these just correspond to these two terms. So how do I do that? Well, I'm going to keep the top equation the same. Minus x plus 2y minus z is equal to positive 9. That's just that equation. And remember, you could write it out. You could rewrite these with x's and y's all the time. I'm just doing this for a little bit of simplicity, and your teacher actually might do it this way. So that's more useful, and I like to do it this way. So how can we eliminate this 3x here, or this 3 right here? Well, what if we took this equation and added it to 3 times this equation? Or another way, we substituted this equation with this equation plus 3 times this equation. So what happens? So we take each of these terms and add to it 3 times each of these terms. So 3x plus 3 times minus x, that is equal to 0. Right? I'm just multiplying this top equation by 3 and adding it to this equation. So minus 3x plus 3x. So let me actually do it one time just so you see what I'm doing. I just multiplied this top equation by 3. So you get minus 3x plus 6y minus 3z is equal to 27. And I'm adding that to this. So minus 3x plus 3x is 0. 6y minus 7y is equal to minus y. And then minus 3z plus minus 2z is equal to minus 5z. This is very computationally intensive, you can tell. And then 27 plus minus 20, that's just equal to 7. And I'm going to dwell on this step a little bit because I really want you to understand what I'm doing. Because if you understood what I just did in this step, you'll understand the rest of this video, frankly. So I just replaced this equation, which is the same thing as this equation, with this equation plus 3 times this. So I said 3 plus 3 times negative 3 is 0. Minus 7 plus 3 times 2 is minus 1. Minus 2 plus 3 times minus 1 is minus 5. Minus 20 plus 3 times 9 is 7. Hopefully that makes sense. So now let's do the same thing here. Let's try to eliminate this 2x. So if you want to eliminate this 2x, we could take this equation and add to it 2 times this equation. So what will happen? We'll have 2 plus 2 times minus 1. That's 0. 2 plus 2 times 2. Well, that's 6. And then we have 1 plus 2 times minus 1. Well, that's minus 1, right? 2 times minus 1 is minus 2. 1 minus 2 is minus 1. And then 2 plus 2 times 9. So that's 2 plus 18, so that's 20. And once again, we could rewrite this, this equation right here. This middle equation right here is the same thing as minus y minus 5z is equal to 7. Just so you remember, this is just another representation of these actual linear equations. I just don't feel like writing the x, y's, and z's and the equal signs. But anyway, now let's see if we can eliminate this term down here. So how could we do that? Well, we could add this equation, we could substitute this equation with this equation plus 6 times this one, right? Because if you have this plus 6 times this, you'd have 6 minus 6, and you would get a 0 here. So let's do that. So let's write the augmented matrix. We're not changing the top line, so we get minus 1x plus 2y minus z is equal to 9. We're actually not even changing this equation, so we're getting 0x minus y minus 5z is equal to 7. And now we're replacing this with this plus 6 times this. So the 0 plus 6 times 0 is 0. 6 plus 6 times minus 1, that's 6 minus 6, that's 0. Minus 1 plus 6 times minus 5, that's minus 1 minus 30, so that's minus 31. And then we have 20 plus 6 times 7. So that's 6 times 7 is 42, so that's 62. Now we're actually almost done solving. What can we do here? So I just want to make sure you understand our representation. What is this last equation? This, 0, 0, minus 31, line 62. Well, this last equation is just minus 31z is equal to 62. And so we can divide both sides of this equation by minus 31, and we'd get z is equal to minus 2. But if we were to do that using our augmented matrix notation, we would just say, well, let's just divide both sides of this bottom equation by minus 31, and we would get nothing happens. Minus 1, 2, minus 1, 9, 0, minus 1, minus 5, 7. So we're dividing this one by minus 31. So it's 0, 0, 1, minus 2. And there you have it. So we have at least solved for z, right? This equation is the same thing as this one. Z is equal to minus 2. Now at this point, what we have just done using this augmented matrix, this is called Gaussian elimination. Now we could continue this, and we can eliminate this term, this term, and this term, and then it would be called Gauss-Jordan elimination. Or we could use the fact that z is equal to minus 2, and then we could substitute back into this equation to solve for y, and then we'd have our values for y and z, and we could substitute back into this equation. And let's do it that way, just for kicks. So this is called upper row echelon form. I always forget the terminology, but let's keep this equation in mind, and let me erase all of this so we have some room to work with. Some room to work with. Can't do anything without some room to work with. Let me even erase this up here. And as you can tell, this is very computationally intensive, and it's not my cup of tea. It's not what I would want to do if I had the weekend to myself. But anyway, let me write these equations in kind of this format so we can kind of go back to our traditional world. So this equation right here, that's actually the same equation. We never changed it. Minus x plus 2y minus z is equal to 9. This equation is minus y minus 5z is equal to 7. And then this equation is z is equal to minus 2. So this, we solved for z. This equation essentially solves for z. And now we can substitute back into this one. So we have minus y minus 5 times z, which is minus 2, is equal to 7. So minus y plus 10 is equal to 7. Minus y is equal to minus 3. Y is equal to 3. There we have it. We solved for z and y. And now we could substitute the y, the z, into this top equation and solve for x. So what do we have? And then we're done. We're at, let's see, minus x plus 2 times y, so 2 times 3, minus z, minus 2, that's z, is equal to 9. So minus x plus 6 plus 4 is equal to 9. Minus x plus 10 is equal to 9. Minus x is equal to minus 1, or x is equal to 1. So the solution, oh my god, my phone is ringing. So many people call me. I think it's my wife. She might be downstairs. We're supposed to go eat out. But anyway, let me just finish this. So the solution to this 3 by 3 equation is the point x is equal to 1, y is equal to 3, and z is equal to minus 2. And that's the unique point in three-dimensional space that lies on all three of these planes, or the unique point where these three planes intersect. Anyway, I hope you got that, and it's time for me to go have dinner with my wife. See you soon.